Welcome to the Data Science Seminar. I'm pleased to introduce our speaker today, Jose Magallanes. Jose has been working with the eScience Institute for the better part of a decade at this point. If you don't know Jose, he's currently a full professor at the Department of Social Sciences in Pontificia Catolica del Peru. As you can imagine, that's in Peru, where he is also the director of the Institute for Social Analytics and Strategic Intelligence. He has been an eScience senior data scientist and visiting professor in computational public policy in the Evans School since 2015. I was right, the better part of a decade, almost exactly a decade.
Oh my God.
Yeah. And I don't know if you didn't know this, he has been up here for many of the winters doing a summer school, right?
Right.
It's
winter school.
a winter school, but for you, it's summer down there,
For me,
right?
it's summer, right?
So he comes up here in the winter to teach people up here while it's summer down there. Go figure. Professor Magallanes has 2 doctoral degrees, one in computational social science from George Mason and one in psychology from Universidad Nacional de San Marcos. And he holds a master's degree in political science and public management from Pontificia Universidad Catolica del Peru, also in Peru. He will join us today to talk about a gentle introduction into networks analysis using R. I will let you get on with it, Jose.
All right. Well, hi, everybody. Well, I hope you like this presentation. I send this to David and the team because, I don't know, people sometimes speak of networks, social networks a lot. And sometimes you want to decide if you go using R or using Python. So I thought that it would be a good idea, what I propose, right, to give you a brief look, a glimpse on the similarities and differences in using R or Python for basic network analytics. So as you see in here in my map, right, this is the plan for this for the coming minutes. I'm going to talk about I'm going to give you some details about network creation, network attributes, network exploration, network nodes exploration, network communities, and network exporting. Right? So it's when I was preparing this, I say, oh my God. It can be a lot. I hope I made a good summary for you guys. There is if you would like to play, I am going to give you just slides, just snapshots of code or things that are produced. But I have a GitHub repo that I can share with you if you would like to go over this and take a look at the Python code or the R code. It is actually, I can give you the link to this map, which actually shows you where everything is on the GitHub repo, right? So let me talk about this section on network creation first, okay? In general, one of the first barriers sometimes is that you don't have the network ready to be at hand, right? So you need to think in a creative way how you are going to have a network, right? So sometimes, for example, I decided to go to use this. I found a while ago, and I'm telling you a while ago because now my developer account in Twitter just give me limited access. But before when I have more access to different functionalities in Twitter or X today, I was able to do some things that I couldn't do last week when I was trying to do something to update the state. But anyway, the example is the same, right? Because I have here the source of this information, right? So there was this web page where it still exists, where you have the 50 influential people in Seattle, right? So you can find a list like this, like with people like where they are showing their names, and you see also their Twitter accounts or the X account, right? So whenever you have a situation like this, it's not that you have a network, but maybe if you are aware that there are some particular functionalities in the Twitter API, you might be tempted to go and build a network, right? So if you have since you already had in this web page, right, the Twitter accounts, right, you can go and you can scrape this web page and you recover. Since you see a pattern, follow Rick Barton, follow Todd Bishon, or follow Sean Akosi, okay? So when you find a pattern, then you can do some nice scraping, right? So let me see, for example, right? There is Python has an R, they have these interesting functions that can talk to the Twitter API. In Python, there is the TweetPy, okay, package that has the function get friendship, and in R, you have the one who is look at friendships, right? So in this situation, if you input those usernames, right, you can find if there is a relationship in these cases. Both functions work the same because they talk to the Twitter API, all right? So you can, for every combination of those of these users, right, you will have a column with all of these usernames, right? And you can prepare all the combinations by pairs. And then you can verify if there is or not a relationship of following one, if there is a friendship between, right? So that would be an easy way to start preparing your network. And once you have it, okay, the good thing is it was not a big network, so it didn't take much time, right? You can start preparing your data, right? So the particular alternative to preparing the data can be, you can have different alternatives. For example, let me show you. Two that are very, very common, right? For example, in the case of the API, right, you can make these two columns, these edges, right? The source or target, or node 1, node 2, you can call it way. But these are all the pairs, right? All the guys who, in fact, had a friendship. This is not all the combinations from the web page. It is just the combinations of people who have a friendship in the web page, in Twitter, right? So that is you have this particular structure, but also if you forget about this situation, sometimes when you do some field work or do some interviews or things like that, okay, maybe you are tempted to have something like this, like an adjacency data frame, or a data frame where you have all the possibilities in the rows and in the columns, and then whenever you find a one, that means that there is a relationship, right? There is a friendship. Right? So these are alternatives, as I was telling you. And also, you might have the possibility of having, I don't know, some attributes, right? So if you know all the vertices or all the nodes, you can have some information particular to that node, right? Like being male or like having some followers. So those are the alternatives, okay? And in my case, right, or our case, you will prepare an Excel like this. So I am going to read the data from here. This is just a Google sheet, right? So we can read this, right? So let me show you. You know, the reading data frames, right? I'm going to, if I have this in my GitHub account, okay, in the repo you would like to see, I just copy the link of that an Excel file there where I downloaded this information. All right, and then if the file link is that one, this is I save this text of the link as a file link. I can go to Python or I can go to R, right? And this is where the action starts. So because in general, when we do statistics in Python or R, we're most of the time using data frames, all right? But now that we're going to build a network, we are going to leave the data frame. So we're going to have as an input a data frame, but we're going to find a new structure, right? In these new structures, we gotta be aware that there are not everything that used to work in the data frame or the basic structures of R or Python offers are gonna work, right? So these are simple data frames where I read the edges that I show you or the adjacency that I show you, right? I just open these two just to show you that there is no difference, right? So there are particular functions if you want to, if you have the data in this way or the other. You don't need to have the data in both ways, right? But if for some reason you have the data in this way or the other, of course, if you have other data, right? If you're already aware of you being a user of, I don't know, UCNet or Payec, right? Of course, R and Python will offer you a way to operate, right? I just mean that showing you this, that if you build a data frame with something that like scraping a website to get some usernames, you just build a well-known data frame and then you will use that structure to build your node, right? Well, I will use pandas here. I will use RAO here or Rio here, right? To import the data. There are these options, of course, to say which of the sheets you want, edges, agency attributes. Those are the names you saw here, right? That will be pretty simple. One advantage in reading the adjacency in pandas, right? That you can do that I couldn't find in Rio when you import it, is that you can tell in pandas if there is a column that will serve as the index, right? So if you don't say that, this will be the first column. But if you say in pandas that the first column is the index, it will be the index, right? That will be the index. And that's very important for the next part, right? In the case of Python, all right, you will abandon the data frame and to build a network, you will use networks, right? And in the case of R, you will abandon the data frame and you will build a network that is going to be an iGraph structure, right? So these are the two ones I am just presenting to you. Okay. All right. So let's create the networks, right? So you know I have edges. The codes for the edges are very simple, right? There is no much difference between pandas and R, between Python and R. So networkx is the function for networkx is net, and the function for iGraph is graph from data frame, and here's from pandas edge list. Okay, so I input the edges. Since my edges are not directed, so I don't networks will recognize that. But in R, I will need to be specific, that telling that it is not directed. Okay. Otherwise, it will create a directed. Okay. So when you my network in Python, networkx will create something like this, right? There is a network class. I have 46 nodes and 393 edges. All right. And when you create it in iGraph, you will see this structure like this. All right. Don't pay attention to this code. All right. That's not necessary. iGraph will also tell you that. It will tell you that this undirected. All right. And the same amount of nodes and edges. All right. There is, well, they say the vertices have attributes which are of type character. All right. If you use the adjacency, right, Python directly will just create a graph for an adjacency. All right. And as I told you, the fact that pandas offer you a way to say which was the index helps, reduces the amount of code, because in R you will need to do some cleaning or some pre-processing, right, in order to tell that in the data frame of the adjacency information data, all right, that will be the wrong names, all right, and then you will need to get rid of. Okay. And then you will just use graph adjacency, and of course you will save the modus and the rest. All right. If you use if you use this one or use this one, it doesn't matter, right? Because we will get the same thing as before. You will get the same structure before. There's nothing different. You can start working from that step on. All right. Now, let me go. Let's keep traveling. So let's talk about attributes, all right? We have already the network. We created a network with the information we have here, but there are some attributes that are not part of that because we haven't used this data frame, all right? In Python, if you're familiar with Python, Python will, in the case of network X, you will need to rely on dictionaries, okay? This is the way that Python prepares the data using dictionary. So it's like making sure, right, that the attribute goes to the right place, because you have to tell, okay, tell me the name of the node, tell me what attribute you want, tell me the name of the node and the attribute you want, right? And something similar for the case of edges, all right? So you will have like two steps. You will need to prepare your dictionaries for the nodes or for the edges, all right? And you will need to then set the attribute. There is a particular function. This is not a network X functions. This is just basic Python, all right? And then you will set the attributes with the edges you create, all right? So this is the network, and this is the edges, the dictionary you created, and here's the name of the attribute, all right? And the same thing about the relationship. Something important to tell you is that in the case of the edges, okay, those links, right? Immediately Python creates the attribute weight. Okay, so the attribute weight is going to be 1, okay, by default. So it's going to be immediately created. I'm telling you this because in R it will not happen. So the attribute weight will not exist. I am going to show you how to create it anyway, right? Because it's very simple. So what if this is the node, the attribute, the dictionary of attribute you created, the node and the attribute, the node and the edge and the attribute, all right? This is going to be the input for the function to set the attributes. Okay, this one, right? And when you set the attributes, okay, you will see that you have, for example, you have the attributes mail and followers. I included those one, and you will see them here, right? So this is how network X is organizing. And since you know attributes are very, sorry, dictionaries are very flexible, you can have a whatever combination of attributes here, right? The most complex one, all right? Like the ones you get when you get a user from any social network API, right? And as I was mentioning in the case of the edges in network X, I created something that is type of relationship. I just wrote tech just to write something, right? And I didn't create the weight was already created, okay? And it is one for everybody. All right. So let me go in the case of R, right? In the case of R, something familiar will come because you will create edges using just vectors, all right? So you say E for edges. Again, the edges of EliteNet are going to have this this attribute, and it's going to be equal to 1, okay? And the nodes, the mail is going to be the attributes mail, and the elite followers are going to be just the followers. The only thing that you need to be aware in the case of, in this case, is that it is not doing any merge or matching, right? If you have the nodes in a different order, you know, then in this case, you might give an attribute, a node the wrong attribute, right? While Python is making sure that you give the attribute to the right person because it's building dictionaries that includes the node and the attribute you want, all right? You don't say the name of the attribute in the dictionary. You will say the name of the attribute here in the setting nodes or the setting edge attributes, right? And as I said, I needed to create the weight because I didn't have weight before. All right. When you have that, all right, you can just request a summary of the net. Okay, and they will tell you the same thing, but now they will tell you that besides having the name of the vertex, all right, there is an attribute that's male. Okay, for the vertex, there is a numeric value, 0 or 1, or followers, that's the same thing. All right. And there is an attribute weight that is for the edges, that is numeric value. All right. So you still, as you see, you can still use the command summary here. If you are in Network X, you don't have a command summary, you don't have a command describe, those commands that are very common in pandas. All right, you don't have that. Let me see. So that's what we have when we say attributes. And when we have attributes, one of the first things we want to do if we have an interesting network is sometimes to explore it using some plotting, right? Okay, so you will need, in this case, for example, right, you can create the color of the nodes based on one of the attributes, okay? And then you have net draw, which is the function that NetworkX offers, right? So that you can plot something like this, okay? And since you have vectors, right, for the nodes or for the edges as attributes, there is this nice library in R, right, gggraph, okay, that will also help you do that, okay? And it works like ggplot with the advantage that you have the geom node and you have the geom edge, right? So when you go and see the NetworkX website, they tell you just in case we are not strong in plotting, all right? So build your network here and go and use something else, right? We can draw things, I tell you, right? But there are more interesting tools to do drawing than NetworkX draw. Right? All right. So in the case of NetworkX, you will need to do some particular coding and then use the draw command, all right? And in the case of R, if you're familiar with ggplot, I believe it will be sooner for you to prepare some nice plot. Right. Let's go and take a look at exploration, right? So there are, if we're going to explore the network, have an idea of what's going on, right, in the network, okay? Maybe we can say something related to connectedness, density, diameter, and assortative, okay? Of course, there are several characteristics of the network, right? But we can pay attention to this. Connectedness, you know, is a network is connected if there is a path between any pair of nodes, all right? The density, right, will go from 0 to 1, where 1 makes it a complete network. There is a link between every pair of nodes, right? The diameter, right, when two vertices are connected, one can reach the other using multiple edges, okay? So the geodesic is the shortest path between two connected vertices. Then the diameter is the maximum geodesic in a node, all right? All right, and the assortativity, all right, the tendency of nodes to connect to vertices with similar properties. Okay. We'll see that. For example, I'm just asking if the network is connected. If it tells me true, that means that the network, there are no subnetworks in all of this. You don't know that, right? Because you don't need to, you are not, I have a network of 50 people, but that doesn't mean that everybody, there is a way for someone to be connected to everybody else, right? To any other person. But in this case, apparently this is possible. Right? There is a particular degree of separation, right? And there is a possibility for anyone to reach another one, all right? If it were false, that means that there is a group in this network, there is another group in the network, and there is no link uniting both, right? So, and that's very easy in both cases. There is not much code, so that's the advantage. In this case, you need to do any particular coding. You just have the function is connecting in both cases. In the case of density, right, is the same thing. Okay, and one thing we need to notice too, right, is that you are getting the same value, right? So the algorithms are implemented in a particular way. Well, in this case, with more decimal precision than in the other case, right? But are still working well. In the case of diameter is 3. Okay, so this is for Python and R, the same function. All right, and assortativity. In the case of assortativity, as I was mentioning, there is this tendency for example, in the case of degree, right? In the case of degree, if it is positive, the value you're going to get, for example, right? It is negative, right? But if it were positive, it means that the nodes with high degree tend to be connected with nodes with high degree. All right. If it is negative, it is the opposite, right? And if it is close to 0, that means that there is no assortativity. In this case, the attribute is degree, right? So in particular, this function exists in both cases. Of course, there is the categorical assortativity. So there is a particular application where you are interested in assortativity, but you want to see if the assortativity related to a particular category, in this case, male, right? So this means in this case, if it were closer to 1 in positive 1, it means that that there is a tendency for men to connect with men. Okay, if it were negative, it would be for men to connect with women, right? And if it is close to 0, all right, there is no such tendency. Speaking of men, right? Python understands well, can translate well the 0, 1. In the case of R, you will need to set it as a factor, right? The nominal assortativity. So that here the name is a little different. Here is attribute assortativity. Here is assortativity nominal, right? As you see, you get the same value. Again, pay attention to this because you need to be telling to several functions in R that the network is the network is directed or not, which in this case it is not. In the case of numerical, that means we just saw the assortativity with the male attribute. Now we'll see with the followers attribute. Our follower is a numeric attribute, right? And so there is a different function, numeric assortativity, and here is just assortativity. All right. So that's a particular. Those are different. All right. Those are different function names. Okay. Attribute, numeric, assortativity nominal, assortativity only, and here degree assortativity and assortativity. All right. But you have all of them in this case. So let's do some node exploration. I guess I'm still good in time. Yes. We can do a lot of things with the nodes, but let me take a look to the well-known metrics in the nodes that are telling you in a way or in different ways the closeness between this eigenvalue. Nodes can have different values of those, and each one is trying to highlight a particular attribute, right? Or trying to tell you if the node has a particular centrality or a particular relevance in the network, right? Is the node close to everybody else? Can he reach easily the rest fastest than the other ones, right? Is this node important to connect other nodes? Is a good bridge, right? Okay. Is this node connected to those who are also good connected? Okay, so that's the idea in this case. All right. So those are the technical definitions, I guess, here, right? And as I tell you, how close a node is to all other nodes in the network. Okay. A technical concept, the average of the shortest path, right? Then from the node to every other node. The betweenness, as I was telling you, the concept of bridge is the measure of the role of a node to act as a bridge along the shortest path between two other nodes. And the eigenvalue is measured based on the importance of the node, right? So all of this will tell you from all of these 50 guys, okay, who look more relevant, more important, all right? And of course, you have these functions, closeness you have in network X and in R, in iGraph. Everything is iGraph on network X, I was telling you. And the same thing for betweenness, all right? And the same for the eigenvalue, okay? Notice that if to get the same values is not straightforward, right? Closeness, in the case of network X, you just request the value and you will get in general normalized values, all right? But you are not scaling the values, right? When you scale the values, that means that the best value will be 1, okay? So you will get all the normalized values. But in R, you have to tell them to be normalized if you want to see the same result as in this case, right? So there are particular attributes you need to make sure that you put there if you want to compare the same thing across Python and R. So in this case, this is not direct. There is no other. It is not as direct before, right? It's other functions. So let's take a look at the exploration of this, right? So in R, right, you will if you have all this or in Python, okay, we will create those data frames. So I mean, if it is going to be you're going to create an attribute for them, right? And the attribute is going to be the between the closer or the eigenvalue, all right? And there is you will need, so you're just creating a data frame. In both cases, you will create a data frame, all right? And then you can plot, okay, for example, okay, this is the betweenness, sorry, yes, this is the closeness and this is the between, right? And you can highlight, for example, right? I am asking in both in Python or in R because I see 2 guys here, right? Todd Fish and Dave Parker, Seattle. Okay. I am requested, tell me who are the top guys, and the same thing I am asking in R, right? And then I can, okay, I can prepare a plot using that information, all right? And you can highlight those guys in the net, right? You can do the same thing. You will need to do the same thing in gggraph. So it looks a little easier, right? And produce something like this. Okay. So sometimes you want to highlight only some particular guy. So it is I like network X in the plotting. So network X, I show you there is a draw function, but network X can also draw in pieces, right? You can draw the edges first, the node first, and then the labels you want, right? That sounds interesting, all right? So you say, okay, I want all the edges, and I want all the nodes, but I don't want all the labels, all right? And so I use the labels that I just found, all right? I'm in the case of a or gggraph, it will be the same, right? It follows kind of gggraph approach. All right. As we get closer to the end, let's talk about communities, all right? Transitivity is this, right? How probable is that 2 nodes with a common connection are also connected, all right? So if you see the presence of triangles, then you start thinking, hey, there are some communities in this place, right? You find that you have the transitivity function in both cases, right? They are not a different name. And you see that it is the probability is higher than 0.5, all right? Is that and this is important, this because sometimes in network you try to think about random networks, right? If there are some communities, it means that it should be kind of far from a random network, all right? So you will hope that this is a little higher, right, than 0.5. It just is that the connection is just not due to flipping a coin, all right? So let me talk about these partitions. There is a lot of things here. So there is a particular, this is a particular strategy, all right, where in Python, okay, sometimes you can say, okay, tell me, when we talk about min cut, okay, tell me the minimum edge cut. So tell me the edge, how many edges I need to take away, the minimum amount of edges to take away, right? So that I cut the network, all right? So it is telling me, okay, if you erase the edge from Dave to tomorrow night and from his structure to tomorrow night, you will have an unconnected network, okay? Okay, so I'll take a look at that. I remove the edges. You see, I'm going to remove the edges from the partition, okay? And then that will be, this will be like my network that is not connected, all right? So I remove that, and what happened is that the node is far, is unconnected, okay? So in fact, having one node away, it already disconnected the network, all right? I wish I had unconnected a series of networks, right? But a group of subgraphs, right? But no, it was just only one node, okay? The important thing here in her, right, is that you pay attention that here, when I am requesting this, all right, I am getting a set, okay? So I am getting a set of tuples, okay? So it is very important when you're dealing with networks in Network X that you are aware of what data structure is coming, right, as the output, right? In some cases, you need dictionaries. In some cases, you will get a dictionary as a result. In some cases like this, you will get a set, okay? Even though the curly braces are right here, remember that Python uses curly braces also to show the existence of a set structure, right? So if I have a set of tuples, what I would like to have, all right, is I am going just to erase some nodes, some edges, sorry, from these, okay? And so what I just to show you, right, you can build a dictionary, because a dictionary of nodes telling the name of the node, it looks like a repetition, right, a redundancy. But I can show you that, but I can also show you here that edges partition, which is this one here, edges partition, these are the edges. I can take away the edges, those edges from the original net, okay, and plot that, right? So I can plot the I can use network X to plot, right, this network without those edges, and I can use these names, right? Remember that I showed you, because I can have labels. I can just use the labels for the ones that I want to highlight. All right. So if we are using sets and dictionaries, that means that the way R will do it is different, because Python R does not have sets or dictionaries, right? So you will get this, for example, all right? When you say, give me the minimum cut. So, okay, Dave Parker on tomorrow night and me the struct on tomorrow night. Okay. Again, this will be the labels of the ones who I am going to highlight. Okay. I can delete the edges, and then I get the lead net cut. That's the original net without these edges. All right. And then I use the set of the labels I showed you. And you get the same result for sure, right? But in this case, all right, you will be using, this is the function ends, right? So when you get this elite net, when you get the min cut, okay, you will use the min cut and you with the elite net, and you will get a matrix. And then you will need to flatten this as a vector. And then you will need to say unique. All right. So this flattening process, I also show you in the previous example, right? Because I need to flatten to get the names of the edges, just to highlight those edges in the network, right? This is the flattening process here, okay? And this is the flattening process here. And it is just because I got edges, and then I just want the names of the vertices of the nodes just to highlight those in the node. All of this process is so imagine the following, right? I am telling you delete some edges, okay, so they can cut the network, right? But the fact of a node to have the capacity to cut the network, all right, gives them some relevance, some importance, all right. So and the fact that the network can be divided because I find some particular edge, all right. If we have this property of betweenness, right? That means that maybe that if I can find the betweenness of the nodes, those are the nodes I should aim to delete in order to see if I can partition the node. Because at the end, if I say that there is a community, it's because there might be a way to partition the network, right? So what we just did is what the Girvan-Newman algorithm does, all right? So you don't need to do all the things I did before. You just apply the Girvan-Newman, okay? And then you get this result, okay? They will tell you that there are two communities if you go for one round, okay? So the Girvan-Newman, okay, the Girvan-Newman is an iterative process, right? So it will try to cut as much as possible, all right, until all the nodes, all the networks appear. You need to say how many communities you would like to have, okay? So if I say just give me the first cut, that means that the first time you cut, okay, this is what I got, okay? This is green, this is gray. That means that I have two nodes, okay? But this network is just one node. And the same thing happens. You also have the Girvan-Newman, but in the case of network X, the function that is in network X is community Girvan-Newman, the direct name of the creator of the algorithm, of the creators of the algorithm. While in R, it is H betweenness community, okay? Because that's the actual the function that is being used for this. In Python, since and the Girvan-Newman allows you also to change the function. If you don't want to use betweenness, you can use closeness or eigenvalue, right? So if I ask the same thing, give me the first cut, all right, you will have something like this, okay? In this case, it looked better, different color, right? Alternatively, than following this approach of cutting edges, there is a very famous algorithm. That's the Louvain method, all right? Okay, where also you're invited to take a look at the algorithm, but the algorithm will detect all the possible communities in the network based on a measure of modularity, right? So what it tries to see is when a particular combination of nodes is good enough, has a particular tendency to be together, but it's like doing some clustering technique, right? Okay, the modularity of being them together is so high that it's better that they are in this cluster and not in the other, right? So it is, although it looks more complicated than the Girvan-Newman, it is actually faster, the implementation in both cases, right? In the case of Python, is Louvain communities, and in the case of R is a cluster Louvain, okay? You will get the same result in both cases. As I was mentioning, the concept of modularity, right? Since I have, I don't know, I believe I have, you will need to run it. If I run it again, it will be different, but imagine I have 5 communities here, right? Imagine I have 5 communities. So I'm going to test the modularity of the Girvan-Newman for 5 communities, or the same amount of communities that we have in Louvain. So I am testing, right? The higher the modularity, the better. So the Girvan-Newman is giving you 0.01, and the Louvain is telling you 0.1. So in terms of modularity, the result of a Girvan of Louvain is much higher than in the case of the Girvan-Newman, right? And the same thing can be applied, the same thing is calculated almost in this case, right? And if you see difference here, right, because I rerun it again and I just paste it, but you will get the same thing. I didn't paste it here. I should have pasted it. All right, and finally, before Dave rings the bell, it's about exporting, right? As well, we have. I could add the partition I created with Louvain, Gibran Newman to the network, and I can save the network. And the same thing for R, right? So I'm sharing you here how I prepare the attributes in Gilbert Newman. So this is a node and this is the group it belongs. So that's what is coming. That's what is going. So that's what I am setting the attribute here, right? And then you just go and save it as a GraphML, for example. I tend to use GraphML because when then you export, let me see. Let me see that thing. Sorry. Okay, desktop one. So, can you see in Gephi? Can you confirm? I hope you're seeing Gephi.
No, I don't think so.
You're not?
Yeah. Okay, good. Yes.
Yes. Okay. Yeah, I just saved the network as a GraphML, so you can just open a Gephi thing, and then you can start playing, right? And then sometimes it's a more comfortable thing. You can come here, modularity, for example, the modularity here is the Louvain method, but I already have it, right? So I can say Louvain partition, I apply the colors, right? And then something people like is start playing with all the different layouts, right? That network that Gephi offers, right? So that's a good alternative, right? To the ones to these more static techniques, right? Well, Dave, I hope people. I hope I didn't interrupt people sleeping, and I hope you like what you just saw. Thank you very much for your time.
I'm not sure how well you can hear that. That's pretty significant applause for this room. So questions for Jose. I have a question for you because I have not seen that software that you were using to present to us before. What is that?
That's a mind map.
Okay.
Yeah, so it's MindMeister. I can send you the link later. People who want to visit that, and there is the link to it. So it allows me just to create like a story in an easier way than I don't know. I love it.
And I'll remind folks online that you can use the Q&A button to ask questions. Questions from in the room. Yeah, Jacob. How would I look at relationships? Got it. So yeah, let me rephrase for Jose. So, oh, you heard it?
No, I couldn't.
Okay, so the question was, what if I have two different networks, say a network of human relationships and a network of pet relationships, and I want to compare those two networks to understand how human relationships might impact pet relationships or vice versa.
But I mean, you say what? You say one about humans and the other one about what? One about humans and the other one's about what?
Oh, pets. It's like a network of pet interactions. So I have two networks.
Okay.
Yeah, like dogs, or yeah, like I take my dog to the dog park, and do they interact with the same people?
Yeah, but because the thing is that if you I imagine that you are a community of people, right? That own dogs, right? And you go to the park and you walk the dog there, right? And it's the creativity, right? Because you can say, I am going to make a network as long as my dog plays with your dog, okay? All right. So if my dog plays with your dog, we are a network, okay? Or if I hire somebody, right, to walk the dog. All right. If two people hire the same person, they are connected through that person, right? So I mean, you need to have a way to connect the networks, right? Because otherwise, if the pets are alone in the universe, just walking by, right? And there is no way for the only thing I can tell you is that if for some reason we are observing in the wilderness, right, in the jungle, some animals, right, that how they interact with each other and they have a particular name, and like a community of gorillas, for example, and we analyze another native community somewhere, right? What we can do is just to have the basic descriptives of networks to see if the diameter or the transitivity or things like that, right? In that case, I can say which one is more interactive or more prone to have communities, right? But they will not be connected. I'll just be saying some particular social difference.
Any other questions from the audience? Yeah, Hamoud.
Thank you for the talk. We'd love to know your thoughts on how do we deal with really big networks? The network is not being effective.
Okay.
That's like the best way to for a really big network, a lot of them.
Great. Can you help me by defining a really big network for you, Hamoud?
50
Million.
50K is really big.
Okay. So Jose, the question is for really large networks, are these tools useful in your experience? And for this individual, they described a really large network of about 50,000 nodes. Although I know their science and 50 million is more their size. But what do you think? Are these tools useful at the scale of 50,000, 500,000, 50 million nodes? Where do we start to need other computational resources than our laptop for these tools?
Oh yeah. Like in any other case, as long as soon this increases, if you have problem with big data, which is just a table, you will have more trouble in a network, right? So that's the first thing. It says if you believe you're in trouble with 100,000 rows, you will be in trouble with 100,000 nodes, okay? Because this imagine the following: in your table, you're just having the attributes of the nodes. In the network, you have the nodes and the attributes and the edges, okay? And the attributes of the edges. So that's different. And you have also all the connectivity among the nodes, okay? So that doesn't mean that it is not relevant because we're all the time trying to find communities, right? We're all the time trying to, as we did it before, right? How can I tell you? What we need to think is why would we analyze 1 million people, right? Maybe in Twitter, maybe in Facebook, right? But imagine that most of the people I have dealt with are doing this in crime, right? So in mafia analysis and terrorism analysis, right? And so those networks are not that huge, all right? And that's why it is important to find key actors and make a decision about that. But at the end, you can do it with as many nodes as needed, but you will need to have parallel computing and other resources because it will take time. And again, of course, related to the question, right? For example, in those situations, you realize that algorithms like the Gerbang-Newman, right? For example, they will be totally inefficient, right? Well, Luban or other algorithms will be much better to detect communities.
Great. Thank you very much. Well, let's thank our speaker one more time.
Thank you.
Thank you, Jose, and thank you all for joining us today. We will see you next Thursday, and thank you. Have a great rest of your day, Jose.
Nice to see you, Dave. Take care. Say hello to everybody.